Welcome back, everyone. In this lecture, we're going to go over the solutions for the recurrent neural network exercise questions. Let's get started. Okay, here we are at the exercise notebook. Let's go ahead and begin. First, we need to import pandas as PD, and then we're going to do a little bit of plotting. So we'll import matplotlib.pyplot as PLT, and then just in case, depending on your version of the notebook, you may need to set matplotlib inline. And I don't believe we use NumPy, but you can go ahead and import it anyways. Okay, so the data set. Remember, our goal is to forecast into the future the actual production of frozen dessert. First things first, we're going to read in this data set. We'll say df is equal to pd read CSV, and it's located underneath our data folder. So you can provide the full file path depending where you're located on your computer. And it's called frozen dessert production. You should be able to tab autocomplete this. And then, just as mentioned in the lecture, we actually want to go ahead and set our index column equal to date, and then we'll say parse dates is equal to true. So that allows me to then just read it in all in one step with the date as a date timestamp as the index. Now, this series of letters and numbers, kind of hard to remember, so we'll go ahead and change the column name to production. So we'll say df.columns is equal to, and as a list we pass in production. There we go. So we get that result. Go ahead and plot out the time series. You could just simply say df plot. You can also edit the figure size if you want. So if you wanted to, you could say fig size is equal to, and then play around with this till it's something meaningful to you. But obviously there's clear seasonality during the summer months, so let's explore that further. Next, we want to figure out our train test split. So the first task is to figure out, well, how much data do I actually have to play with? So we'll say, what's the length of my data frame? It's 573 points. So our next task is to split the data into a train test split. And in our particular case, we told you the test set should be the last 24 months of data. That's something you could play around with, but it should at least include 12 months of data, which is a seasonal cycle. We'll go ahead and make it larger to be 2 years of data. So we'll say test size is equal to 24. And then our test index is then equal to the length of the data frame minus the test size. And what's nice about this equation is then you can play around with your test size and edit the test index as you see fit. And then our training set is simply starting from the very beginning, go all the way up to that test index. And then our test set is essentially the end of that. So it says starting at the test index, go all the way to the end. Okay. So we have our training set and our test set. If you check the length of the test set, it's 24 months. So essentially what our model is going to be doing is based off most of the data set, essentially everything up to the last 2 years, see if you can forecast into the future 2 years, which is our test set. Okay, so next it's up to us to scale the data. So we'll say from sklearn.preprocessing import min-max scalar. Go ahead and run that. Create our scalar object. Scalar is equal to an instance of min-max scalar. And then we only fit to the training data because we don't want to assume that we have prior information about the future. So we'll say fit to our training data. Technically, this could be a fit transform if you wanted to do it all in one step, but I like separating it out into 2 steps just for readability. So scaled train, scalar.transform, transform our training set, and we also have to make sure to transform our test set. So scalar.transform on the test set. Okay, so we have our scaled data. Next step is to create our time series generator. So the first generator to create is for the actual training data. We'll say from tensorflow.keras.preprocessing.sequence import time series generator. And we'll say, there we go. I just tabbed auto-completed that. And the length of our actual training is up to us, but we said at a minimum it should be 18 months to give length to capture kind of the full year seasonality. So we'll say that the length of the batches is 18 months. How many actual features are we working with? Well, it's just one feature. And you can define it here or define it later. Remember, we eventually passed it in upon creating the model. And now it's time to create our time series generator. We simply pass in our scale training set. That's the source of both our X and Y. The length is just equal to the length of the batch. Remember, that's how many months are included in each batch. And then the batch size will just be 1. We'll just do kind of one set at a time. And you can do generator indexed at 0 to see what the example batches look like. We did that in the lectures. Okay, next it's time to create the model. So we'll say from TensorFlow.keras.models import sequential, and then from TensorFlow.keras.layers, we need to import 2 types of layers. One is the LSTM unit layer that we're going to be using, and for the final output layer, it needs to be a dense layer. And now we'll define our model. So model is equal to sequential model.add, and I'll add in 100 LSTM units here. And then we'll make sure that the input shape is defined correctly. We'll say input shape is equal to length, whoops, make sure that's in a tuple, length by n number of features. Finally, you have to make sure to add in the dense layer. So we'll say model add in our dense layer. This should just be 1 neuron since we're predicting just 1 output. And then after that, we'll compile the model. So we say model.compile, optimizer, go ahead and choose atom, and then the loss is mean squared error. You can play around with the optimizer as well. That doesn't have to be the atom string. You have a lot of options there. Let's run this, make sure we didn't commit any typos. It's created the model, and to see a summary of the model, you can say model.summary, and we see the output here. Okay. Next, we want to create a generator for the scale test / validation set. So just as we did in the lecture, I will say my validation generator is equal to a time series generator, except this time it's based off the scaled test data. So scale test data, and then the length is the same as before, and then the batch size will also be the same as before. And whoops, make sure batch size, I forgot to define it, so I'll just hard code it as 1. Okay, so probably a good idea is to just set a variable batch size up above. That way you can play around with the batch sizes, but typically 1 works really well for time series data. Next, we want to create an early stopping callback based off validation loss. We do this by saying from TensorFlow.keras.callbacks import early stopping, and then we'll create our early stop is equal to early stopping, and what we're going to be monitoring here is validation loss. And I recommend to have a little higher patience when it comes to recurrent neural networks. Obviously, there's no right answer here. You can always play around with this, but I'll go ahead and say just wait for 2 epochs. Then we want to fit the model to the generator and let the early stopping dictate how long we're actually going to train for. So we'll say model.fit to a generator, pass in that training generator created, choose some arbitrarily kind of high number of epochs. The validation data should be linked to your validation generator. And then finally, don't forget your callbacks list to make sure we actually implement the early stop. So let's go ahead and run this. I'm going to comment out that previous cell to make sure we don't get any typos here. Run that. Okay, so now it's fitting to the generator. In the solutions notebook, we went ahead and the only difference that we've done so far is we told the LSTM to use an activation unit of rectified linear units. Here I'm just using the default, which is the hyperbolic tangent, I believe. We do Shift Tab here, it will tell us. But what we're going to do is we'll fast forward into the future until this is done training on whatever epochs are dictated by early stop. So let me hop forward into the future until this is done training. All right, this is finished training for me. It trained pretty fast, just in 4 epochs. Depending on the activation functions and the number of neurons you choose, it may take longer. But we'll go ahead and just plot our losses. So let's go ahead and do that. We'll say loss is equal to pd.dataframe model.history.history, and then say loss.plot. Run that, and we can see here that it looks like our training loss was starting to go down more, but our validation loss was starting to peak, and due to our patience value, it ended up just stopping training there. Okay, the next step is to evaluate on our test data. So we're going to forecast predictions into the test data range. And That may be slightly different depending on what you chose, but recall that our test data set, if we come back up here, it should actually be 24 months. So we come back up here and we decided that the test length was 24 months. So let's go ahead and do that. And what we'll type out here will be the following. And I'll do this by hand because this is probably the trickiest part to understand of the entire lecture. The rest is pretty straightforward once you get used to it. But I set an empty holder for my test predictions. Let me comment out that cell so we get a bunch of room here and create an empty cell. Okay, so first thing, I want to keep track of my test predictions. And then the next idea is I have to figure out what does the first evaluation batch look like. So what do I first pass in to my model and say, hey, give me 1 month into the future? Well, that should be the very last possible batch in my scaled training set. So that'll be scaled training data minus the length of my batch all the way to the end. So for example, if I was predicting, if my model took in 24 months to predict the 25th month, 1 month into the future, then this would be the last 24 months of my training data so that the next month is the first point in my test data. So there's my first evaluation batch, and I'll set it to my current batch. The one thing I need to make sure to do is to make sure it's in the correct shape. So that's first evaluation batch reshaped to the following, and we pass in a tuple here. Notice the double parentheses. It's just one time series per batch, so it's essentially batch size by the length, which in our case was that 18 months. And then the number of features is just 1. And if you want to play around with the batch size, this 1 would be batch size. So that's what this represents. Then we have for I in range, length of test, because we're only forecasting onto the test set. Then I need to get a prediction 1 timestamp ahead. So I'll tell my model, go ahead and predict based off the current batch information. And at the very first pass, that's essentially saying, hey, given the last 24 months of the training data, what does the first month of the test data look like? And to get the first month of test data, because of the way the formatting works out and the way it returns it, we index just 0 there. And you can print these out in case you're ever confused. So say my current prediction is this. So I would recommend if this is still confusing you, just go ahead and put a bunch of print statements here. Print out the entire prediction and just do a range of 1. See what happens in 1 loop. Okay, then I want to store that prediction. So I say my test predictions, go ahead and append my current prediction. And then finally, I need to update my current batch to now drop that very first value and then add in the current prediction value. So now my current batch is essentially moving 1 month into the future. So I'll say np append, and this is essentially where the NumPy indexing gets a little tricky. So we'll explain it one more time for you. So it's a 3-dimensional object where we have batch size by length by number of features. The batch size isn't actually changing, so we'll say grab everything from the entire batch, because it's just 1 time series, comma, and then for the length, I want to say grab everything but index 0, because that's essentially what I'm dropping. So I say 1 colon. And then the number of features hasn't changed, so just grab everything there. And then what I'm going to do here is I want to append my current prediction. So we'll say current prediction. And the reason I pass it with these double set of brackets is to make sure the dimensions make sense for where I'm actually inserting it. And I need to insert it in index 1 here of my shape. So we'll say axes is equal to 1. Okay, so this is probably the hardest line to understand, but really it's just reaching into the NumPy array and make sure that the dimensions line up. We're not editing the batch, we're not editing the features, we're editing the shape at index 1, which is this guy right here. And we say 1 colon because I drop that very first item in my true train data, and then I append in my current prediction. All right, so that's my current batch, and that's actually it for the loop. So we'll go ahead and delete these spare lines. And let's run this, make sure I didn't commit any typos. And whoops, we actually forgot to import NumPy. So we'll do that as well, import NumPy as NP. Now we'll run it, and there we have it. Okay, so we can see our test predictions. Recall that our test predictions are still scaled, so we need to inverse transform them. So we'll go ahead and do that. we'll say scalar dot inverse transform our test predictions, and then I'll call these my true predictions. So there are my true predictions, and let's append that to our original test data frame by creating a new column called predictions is equal to true predictions. You may get a warning here. Again, you can ignore it. So if we insert one more cell below and then take a look at test, I now have my true production numbers against my predictions. Okay, so my predictions, it looks like more or less they're getting the same trend, but these do look like they're pretty noisy. So let's see how well we actually performed here. So we'll come back, we'll plot our true predictions versus our true test values here. So we'll say test.plot, run that, and it looks like our predictions are not really matching up that well to our production. So we also want to calculate our root mean squared error. Let's do this. So how can we actually do this? We simply say from sklearn.metrics import mean squared error, and then you can say the mean squared error, compare your production versus your predictions. That's the mean squared error, so the root mean squared error would be NP SQRT. Run that, and so right now our mean squared error is 29 units, and you can check out the units by coming up here and seeing what the actual units are in. Okay, so is this a good enough model? In our case, just visually we can see that the model's not really good. So what can we begin to do to try to fix this model? Well, there's lots of different options if we come back up here to edit our model itself. So one thing we can do is we can edit the activation function. Another thing we can do is edit the amount of LSTM units. So maybe we decide, hey, 100 units isn't enough to basically grab this behavior, especially since we're trying to predict 24 months to the future. Now, that's another thing you can edit. So coming back up here, maybe using an entire set of 24 is just too much. It's trying to predict 2 years into the future each time. So maybe you decide to change that to 18 for a test size. And that's what's really nice about using these variables is you can easily start playing around with your data. So you decide, I'll change my test size to 18. And then to make sure that's correct, when I'm actually choosing my validation generator, I'll have to edit this because right now, if we take a look at the size of the test set, it's also equal to 18. So maybe I just choose 12 as my length here. And so what I'm going to do is I set my test size to the last 18 months, and my batch size is now 12 months. And so what I can do is I can start rerunning all these, and maybe I add in some more LSTM units if I think that will help. So maybe I add 150. Keep in mind, too many neurons, you're just going to be overfitting to the data. So this is another value you can play around with. Maybe 150 is too much, etc. So let's just go ahead and see if those things fix it. Again, this isn't part of the actual exercise. This is just me exploring further and trying to show you what you would do in real life, the things you can play around with and edit to try to improve your performance. And luckily, we already have this metric that I can improve on. So I can see visually, am I grabbing that seasonality? It looks like the seasonality is being obtained to some degree. And now what I want to make sure is that I obtain that seasonality behavior and try to reduce this number. So a perfect fit would have 0 here as a root mean squared error. So let's do this. I'm going to basically run all these changes. So I'll change my test size to something smaller, essentially allowing my model to have more data to train on. And then we'll rescale everything. The time series generator, what I'm going to do is I set my batch now just to 1 year. And this is pretty much the absolute smallest I can make this. So we'll go ahead and keep it as 12. If I try making it smaller, then I'm not grabbing really that full year information of seasonality. We'll recreate our model, see if adding more neurons helps. Notice that Keras actually updates you and saying, hey, this is the next model you're creating. Redefine our validation generator. We still have our early stopping. And let's go ahead and try this again and see if this works. So I'll fast forward in time until this second attempt works. Okay, so what's interesting here is even with more neurons, that only needed 3 epochs to fit. So that's something that's interesting. Let's go ahead and plot out the loss. Check out that behavior. And here we have it. So there's our validation loss. It may even be worth trying to increase that patience because it's not clear to me that that validation loss was going to keep going down or keep going up. So that's something you can also play around with. Maybe we're actually not training for enough epochs on this. So now it's time to evaluate our test data. We'll go ahead and just run the same series. And we can see here production versus predictions. Notice the actual values have now changed because now my entire test length isn't as large. I'm only doing 18 months instead of 24 months. And now let's go ahead and do the test plot. And now it looks like we're fitting much better to the data. Still not definitely perfect. We can't actually grab that little spike trend that looks to be repeating. It's kind of too smooth right now. But let's go ahead and calculate our mean squared error. I'll rerun these cells. Keep in mind, our previous value was 29. So if we get lower, we improved on it. And now we get 7. So a major improvement. Again, the things that I changed were I gave my data more, or excuse me, I gave my model more data to train on by decreasing the length of that test set, and I gave the model more neurons to have available to it, so 150. Another thing we can do is kind of retrain everything, but see if we give it more patience, because it's kind of surprising that with 3 epochs, it's all I needed for training, given this sort of loss chart. Now, it may be the case that validation loss ends up spiking beyond this, but it's worth actually exploring that with more patience. Main thing I want to clarify for you is there's still a lot more you can do to improve your models. So if you get kind of a crappy fit the first time around, you can always play around with a lot more, such as the length of the test set, the number of neurons in your LSTM layer, the patience in your early stopping, etc., to see how you can continually improve your fit. And for time series information, I would always encourage you to do both a visual check and a quantitative check, such as root mean squared error. I hope that helps you, and I will see you in the next section of the course.